Hello everyone, I am Priyanka Lamba. Today I am presenting a contributed paper entitled Simple and Rapid Eco-Friendly Synthesis of NIO RGO Nanocomposites using Guava Leaf Extract and their Physicochemical Characterization. These are the outlines of my presentation: introduction, then synthesis of graphene oxide, reduction of graphene oxide, synthesis of aqueous extract, synthesis of NIO RGO nanocomposites, then their characterizations, conclusion, and references. So, as we all know, graphene-based multifunctional materials have attracted much attention of researchers for the fabrication of efficient devices like solar cells, sensors, and supercapacitors. And we also know that graphene and its derivative, that is GO, shows larger planar area, good thermal conductivity, chemical stability, higher electron mobility, and excellent mechanical properties. Traditionally, GO is synthesized using Hammer's method by oxidation of graphite powder, and then conductivity of GO is increased by its further reduction using chemical reduction method or thermal reduction method. So, in this context, there are transition metal oxide nanoparticles like nickel oxide nanoparticles and iron oxide nanoparticles can be used as supporting material with RGO, which can restrict the aggregation of isolated RGO sheets. And this kind of hybrid configuration of transition metal oxide nanoparticles and RGO can enhance the performance of material, and these material can be used in many applications like supercapacitors and catalysis applications. So in present work, we have synthesized NIO RGO nanocomposites using a green approach in which we have used guava leaf extract as a reducing agent and capping agent. So first of all, we have synthesized graphene oxide. For synthesis of graphene oxide, we have used modified Hammer's method, and these are the steps which we have followed to synthesize graphene oxide. After preparation of GO, we have reduced GO using chemical reduction method, in which we have used hydrazine hydrate as a reducing agent. Using following steps. For preparation of NIO RGO nanocomposite, we have used guava leaf extract as a reducing agent, and we have synthesized guava leaf extract using these steps. For preparation of NIO RGO nanocomposites, we have used nickel sulfate hexahydrate as a precursor, and guava leaf extract as a reducing agent. After successfully preparation of NIO RGO nanocomposites, we have characterized our samples using UV spectroscopy, X-ray diffraction spectroscopy, Raman spectroscopy, scanning electron microscopy, Fourier transform infrared spectroscopy, X-ray photoelectron spectroscopy, and TG and DTA measurements. These are the results of our work. In XRD study, the XRD spectra of synthesized GO, RGO, and NIO RGO nanocomposite is shown here. For GO, we have observed a sharp peak at 2 theta is equal to 10.91 degree, and corresponding interlayer distance was found to be 0.81097 nanometer. And for RGO, we have observed a broad peak at 2 theta is equal to 24.21 degree. Here, this broad peak shows that crystal phase 002 is randomly arranged in case of RGO as compared to GO. For NIO RGO nanocomposites, we have observed 5 peak. And the 2 theta values are shown in table. Here we can see we have also observed a peak corresponding to RGO at 2 theta is equal to 22.70 degree. And we have also calculated the crystallite size of synthesized nanoparticles by using a Debye-Scherrer formula. These are the SAM images of synthesized geo at different magnifications. From SAM images of geo, we have observed wrinkled and layered flakes on the surface of geo. And in case of RGO, from the SAM images, we can see that RGO contains crumbed sheets, and these are the SAM images of synthesized NIO RGO nanocomposites. In these micrographs, we can see that NIO nanoparticles successfully embedded into RGO sheets. The Raman spectra of synthesized GEO, RGO, and NIO RGO is shown in figure. For GEO, we have observed a D band at 1360.27 centimeter inverse, and G band at 1592.68 centimeter inverse. And intensity ratio of D band and G band is found to be 0.85, and for RGO, intensity ratio is found to be 0.95. Here, increased ratio of ID by Ig shows that occurs due to the restoration of sp2 carbons. And by calculating intensity ratio of D band and G band, we can determine the structural defects. In case of NIO-RGO, we have observed one peak at 514.82 centimeter inverse, which occurs due to the vibration of lattice atoms of NIO. In UV visible spectroscopy, we have observed absorption peak at 264 nanometer for GEO, and there is a shift in absorption peak in case of RGO. And this red shift occurs due to the restoration of sp2 carbon, and it also shows the increment in electron concentration. In NIO RGO nanocomposite, we have observed a broad peak in wavelength range 260 to 270 nanometer, which occurs due to the coupling of NIO nanoparticle and RGO. In XPS analysis, here C1S XPS spectra of GEO and RGO is shown. For GEO, one peak occurs at 282.6 electron volt, which correspond to sp2 carbon components, and peak at 284.45 electron volt correspond to single bond components of hydroxyl group. And we can see that in case of RGO, P correspond to hydroxyl group disappears. These are the Ni2P spectra, Ni2P spectrum, and O1S spectrum, and C1S spectrum of synthesized NIO RGO nanocomposites. And for in Ni2P spectrum of NIO RGO nanocomposite, peak observed at 54.5 electron volt correspond to Ni2P 3 by 2, and peak correspond peak appearing at 870.8 electron volt correspond to Ni2P 1 by 2. And from FTIR spectra, we can see that for GEO, peak corresponding to hydroxyl group is appearing at 3343.42 centimeter inverse, and peak corresponding to carboxyl, and there are some peaks corresponding to carboxyl acid group and epoxy and alloxy groups is, and similarly FTIS spectra of NIO-RGO shows the combined behavior of NIO nanoparticle and RGO. From the DTA measurements of GEO, we have observed first weight loss at 35 degrees centigrade, which is due to the evaporation of water molecules, and second weight loss occurs at temperature range 165 to 220 degrees centigrade. For RGO, first weight loss again occurs due to the evaporation of water molecules at 45 degrees centigrade, and second weight loss occurs at in temperature range 470 to 560 degrees centigrade due to the pyrolysis of hydroxyl and epoxy groups. In DT and TG curve of NIO RGO nanocomposites, there is a weight loss between 700 to 900 degrees centigrade, which correspond to the thermal decomposition of RGO. And here we can see that after 900 degrees centigrade, there is no weight loss, which indicates that thermal decomposition of RGO is completed. So from the characterization results, we can conclude that we have successfully synthesized NIO-RGO nanocomposites using eco-friendly green synthesis approach, in which we have used a non-toxic aqueous physico extract of guava leaves as reducing and capping agent. And these synthesized NIO-RGO nanocomposites can be used as electrode material in supercapacitor applications. These are the references. Thank you for your kind attention.